So today I'm going to be talking about how Teardown is rendered. Basically, this is going to be a preview of a blog post that I'm writing. That's, I'd say about 80%, maybe 90% complete. The rest of it, I'm just gonna wing it. I got RenderDoc open and everything. So, and at any point, feel free to ask questions or point out anything that I missed. You can write in the chat or just unmute and start talking. Basically, feel free to interrupt me at any time. So to start, I'm sure most of you are aware of what Teardown is. It's a physics-based voxel game where the object is to basically plan a heist and carefully carve your way through the level. And it has a pretty interesting ray trace renderer that we're going to be exploring. But first of all, let's talk about my configuration that I used. So for the game, the game has very simple graphics options, and I just turned them to high and disabled all the image effects. And so at the beginning of the frame, it resets most of OpenGL pipeline state. It's not very interesting, but then it copies a texture to an image. And these textures are used for rendering screens. So this is an example of one of those textures on such a screen. And then the next, probably the biggest thing, is the gbuffer path. So Teardown is a deferred renderer, which means instead of rendering and shading all the objects in the same path, it basically renders surface properties of the objects and then shades them in a separate path. So it's split into two main passes. So Teardown uses albedo buffer, a normal buffer, a material buffer, motion, linear depth, and then nonlinear depth. And I'll get into what those are for in a minute, but here you can see albedo, normal, material. Motion is just 0 in the scene because I'm standing still. But that would be like motion vectors for temporal anti-aliasing and such. And then Teardown also records linear depth as well as nonlinear or hyperbolic depth for depth testing. Oh yeah, the material buffer encodes 4 values: reflectivity, and then smoothness, I guess you call it, or 1 minus roughness, metallic, and emissive. So I was curious as to what reflectivity affected, and so I hard-coded some values. Open these. If I force reflectivity to 0, it looks pretty normal, but if I do 50%, everything becomes shiny, and 100%, everything becomes super shiny. Yeah, it seems like it affects a mix between specular and diffuse illumination. Oh, and here's a scene where there's some motion happening. You can see the motion buffer has non-black values. Oh, and I noticed some interesting things about the gbuffer. For example, the albedo, instead of using RGB8 S-norm like most renderers would, it's using a new unorm, 16-bit unorm texture. And I believe they're doing some weird things with color space and color encoding that cause them to lose precision. And so that's why they have to use a 16-bit buffer, because the texture they're reading from for albedo, it's reading from 8-bit textures. And so it's odd that they would need a higher precision output texture. But the reason I believe they need that is because they do a linear to nonlinear sRGB transform in the shader. But that's sort of a detail. I'm not really sure what's up with that. Just thought it was kind of weird. But ultimately the output looked good, so can't really question it too much. Oh, and then also the normal buffer is RGB8 SNorm, which is low precision, but it should be fine since this is a voxel game and all the objects can only be facing one of 6 directions in general. Although technically you can align objects off the grid. But yeah, I gave some more information about that here. So generating the G buffer, made a little video. All right, so that's how they fill the G buffer. What they do is they render the wireframe or the bounding box of each object. Contrary to what some might think, is that they are actually rendering triangles, but these are proxy volumes. And so they render the back face of the triangle or of the surface, and then they trace a ray into the object volume itself. Each object is represented with a 3D texture. Yeah, so that explained. Yeah, they use Voxel DDA, which stands for, I think, digital differential algorithm or something. But basically, Voxel DDA is an algorithm that lets you step through a voxel grid precisely, and that's how they render these 3D shapes inside of these volumes. And so, yeah, let's look at how one such texture looks. So you can see that each layer of the image is one slice of the chair starting from the bottom and going up. And you might also notice that there's different shades of red. It's not just solid or not solid, because the color or the shade of red indicates the material. And that's how you get the different colors on the chair. Visual of the DDA algorithm. This is in chat. Yeah, so the DDA algorithm, start a ray and then it'll traverse all the voxels that the ray touches. It's pretty simple conceptually. Yeah, and feel free to ask any questions you might have, Leslie, if you're still confused.
Well, it reminds me of the render for like Wolfenstein, where it's using grids and then it's tracing the ray. What is it called? The ray, it's not a ray tracer. I forget what it's called.
Oh,
but
raycaster.
Caster, yeah, ray casting, but in a 2D sense.
Yeah,
But
I
it's
guess
just, yeah.
So someone asked about Overdraw. So the way Overdraw is handled, they have a couple strategies. The first one is that they do have depth testing. So what they do there is they render front to back, right, to make sure minimal overdraw. And then, I don't know if I mentioned it, but yes, at certain intervals during this, oh, if you saw this turn black for a second, that's actually a copy where they copied the, I believe, linear depth to another texture, and then they use this linear depth for basically their own early Z test. Because what they're doing in the shader prevents, yeah, I remember they explained this in the stream, but it was really high level. So they're using discard in the shader as well as, what's it called? They're setting the depth manually, which both of which prevent the early depth test from happening. So they have to kind of implement their own like janky early depth test. So what they do is they render a bunch of objects and then they copy the depth to another texture, which they can then read for implementing the early depth. Maybe I can show that in the, well, actually I probably shouldn't. Yeah, I'll show code later. But yeah, they can do basically a depth test before the expensive raycast. And that's kind of how they deal with overdraw. Not pixel depth offset, but rather programmable depth, like setting gl underscore frag depth. Because what they're doing is they're rendering the back face of the geometry, which you can't really see with these cube meshes or rectangular prism meshes. But and the reason for rendering back faces is so that the camera can go inside of a mesh and you'll still, or it can go inside that bounding box of a mesh and you'll still be able to see the object because the back face is being rendered. If that makes sense. Okay, so for material, yeah, they have these textures. They're basically atlases that encode color and other material attributes. And for each model, yeah, explain how this works. The color indicates the index column. Okay, so the red, the shade of red is the column to use in this texture, in each of these textures. And then the quote unquote palette is passed as a uniform variable, which each object has one palette. So row and column. And that's used to sample from the color texture and the material texture. And that's how each object has material. And yeah, if you look really, really closely, you'll see that the entire left column of each texture is empty because 0, the black color, is used to encode empty space. Yeah, and so objects have small details that are created by projecting various maps onto the voxels. I'm not sure the exact encoding they use, but I'm guessing it's something like triplanar projection. But if you play around with it in game, you can sometimes notice that the albedo of like a wall section will change when you damage the wall around it. It's just a funny little artifact. But yeah, these are the textures that they're projecting onto the meshes or onto the voxels to give them this per voxel detail and normals. Oh yes, and I explain how the depth testing thing works. Oh yeah, and frustum culling is clearly used because, as you might notice, during this whole section, only objects that are actually visible in the frustum are rendered. So we can kind of determine that all the objects that weren't rendered were outside of the frustum. And some people are curious about how cables are drawn in Teardown, and they're actually just drawn as simple triangle lists. And as far as I can tell, they're simulated entirely on the CPU, and then I suppose remeshed every frame, or at least every frame that they're changed. After the G-buffer path and the cables, which I guess are part of the G-buffer path, the focal plane is computed, and it's computed by taking several samples around the center of the screen in a spiral. In a spiral, it looks like this. And each sample will reach depth. And then it takes an average to get of the depth to compute a focal plane. And then that focal plane is blended with the previous focal plane to create a final focal plane, which is used for depth of field later on, which is disabled in this frame. After that, they blur the normals using a similar sampling scheme. So this gives a sort of bevel effect of objects. Yeah, it's a little blurred on the corners, but notice how they only blur nearby normals. The normals over here do not get blurred. And you can see the effect here on the gun I'm holding. So after all that is the lighting path. So Teardown uses proxy geometry to draw lights, which that will be explained later on. But that's basically, in short, it's really similar to a classical deferred renderer. So yeah, this is what the lighting looks like. The lighting happens after the G-buffer is rendered, which allows you to shade. And lighting is broken into three major passes: the ambient lighting, the sun lighting, and then the local lights, which are like the lights are actually in the scene. So starting with the ambient light, this is basically, you could think of this as computing ambient occlusion. The way it works is that Teardown shoots two rays in a random direction, well, cosine weighted random direction on the unit hemisphere, and then it also jitters the start of the ray. And the occlusion, I guess, is determined by how far the ray can travel before it gets blocked. And so that provides a pretty good proxy for actual occlusion. So if the ray can only travel a few units before hitting an object, then you can be pretty certain that that pixel is occluded. But if it can travel far, then the pixel is not occluded, and so it receives more ambient lighting. And the ambient lighting is just a solid color. There's no bounce global illumination or anything. It's just a solid color per level. And yeah, I did some experiments with changing the number of samples and the ray distance. First row is one versus 8 rays. So yeah, just a lot less noisy with 8 rays instead of 1. And note that by default, Teardown uses 2 rays per pixel. And then my second experiment was just testing 120 centimeters versus 480 centimeter rays. And the reason the lighting is different is because the occlusion depends on the fraction of the maximum ray distance that the ray could travel before being terminated. And so that's why the shorter ray image looks brighter, because more rays could travel the full distance. Yeah, and so I call it ambient lighting in this post, but it's more like ambient occlusion. Except it is lighting because it is computing the actual lighting from ambient. Yes, I am editing these variables in RenderDoc because I can see all the shaders are not obfuscated in RenderDoc, and you can edit. RenderDoc lets you edit GLSL shaders and recompile and run the entire frame again. A pretty nifty feature. Oh, you cannot replace uniforms. You can't directly edit buffers or uniforms, but you can, since you can change a shader that gives you, that basically lets you replace uniforms in a way, because you can just replace the uniform or where it's used in the shader with something else. Yeah, I'll probably demo that later. But essentially, back to the post, Teardown has 3 main ray tracing functions that it uses. And these functions have a different level of granularity. And they're used for different effects that require different amounts of precision for performance. So yeah, it calls them in the shader, it calls them raycast shadow volume, and then raycast shadow volume sparse, and then raycast shadow volume super sparse. And ambient occlusion or ambient lighting uses super sparse variant because it doesn't really care. Since ambient lighting is super low frequency, you can get away with inaccurate tracing, I guess. And so that's how you can save some performance on this path. Yeah, a quick overview of the super sparse tracing. It's 4 levels. It takes a few steps of a fixed size. And then if it hit no geometry, it'll double the step size and take a few more steps through the volume. And it'll double again, take a few more steps, and they'll sample a higher MIP level, which means, oh, yeah, so the world in Teardown is, I don't know if I have a picture of it actually. Okay, I forgot to include a picture of the world texture, but basically the 3D texture represents the whole world. And it looks approximately like this. And you can step through the slices to see that is indeed the entire world. And it has several MIP levels. The higher MIP levels are lower detail and can be used to see geometry at like a coarse level to see if basically you can read a higher MIP to see if there's the possibility for there to be some geometry in a lower MIP, if that makes sense. It's similar to how high Z occlusion culling works in a way. But yes, Teardown uses the higher MIPS as a proxy for whether or not the voxel is filled. And that's what's being used here in this trace. So the super sparse volume raycasting function, in conclusion, it's basically, it takes a small number of steps. And so it's fast and it manages to travel a pretty far distance without taking a lot of samples. And that's why it's used for ambient lighting. And then after ambient lighting, there's sun lighting. We'll try to take a different capture for this because the previous one was indoors. And this one's pretty simple. At each pixel, or at each surface rather, a ray shot in the direction of the sun, but jittered a little bit to give a nice soft shadow, which might be visible. Kind of hard to see, but you can see some noise on the edge of the shadows. That's the soft shadow. And in this scene in particular uses a constant width penumbra, although the true penumbras that have a varying width based on distance from the occluder can be achieved by changing a uniform variable. So without it, you just have these constant width, constant softness shadows. And if you change it, I increased it a bit, and now you can see that the shadow of this pole, for example, it gets softer farther away from the occluder. I just thought that was a neat little thing. Yeah, so someone asked me how the MIP levels of the world 3D texture is computed, and that's done by taking the max of all the 8 texels below that MIP. So that's why I mean when I say it's similar to high Z buffer generation, because taking the max, because it's being conservative. So the light or the sunlight path uses sparse voxel tracing, which is similar to super sparse method that I talked about earlier, except it's similar in the fact that it's not DDA. So it's taking sort of fixed size steps rather than precisely traversing the grid. But instead of switching between MIP levels at fixed intervals, it dynamically changes MIP levels based on how sparse the grid is. Oh, okay, looks like I forgot to finish this sentence. In short, it will cause the trace to reduce it'll reduce the LOD, basically. And so you can just think of it as a more precise version of the super sparse tracing. Okay, now we're finally onto local lights. So this is, when I say it's like a deferred renderer, a classic deferred renderer specifically, the lights are rendered with proxy geometry. So And by that, I mean spheres and hemispheres. And you can see in the scene the positions of all the lights. And the lights are modeled as area lights. There are no point lights or no punctual lights, like in a typical real-time renderer. And they do use a little jitter to achieve that effect. Oh, and you can also notice that the shadows of very thin objects like this table leg are not perfect due to the fact that they're using sparse tracing rather than the precise grid traversal like they use for rendering the objects themselves. So Teardown has 5 kinds of lights. It has sphere lights, which this is a sphere light. These are all sphere lights. It also has cone lights, which are used to implement spotlights. It has capsule lights, which the only example of an actual capsule light I found was this exit sign on a door. And it also has area lights, which are actually rectangles. And these are used all over the place, mostly for ceiling light and emissive surfaces. And there's also screens, which are the same as area lights, except the output color is attenuated by randomly sampling a pixel on the screen texture. And so light visibility, like determining if a surface can be seen by light, is determined by tracing a ray from that point onto a random spot on the light surface. And if there's any voxels in its path, then it will be obscured and uses a sparse tracing method. And the light attenuation, I wrote a whole paragraph on it, but it's not really that special. It's basically based on the ray distance, as you'd expect. So the farther the ray travels, obviously the darker the light coming from the surface will be. After this, there is spatiotemporal denoising, which it sounds very scary, but I'll explain it. I'll try to explain it. So as you've probably seen, there's a lot of noise in the lighting buffer, so like right here, this is basically what we're working with. This is a super noisy image. And so to reduce that, we use spatiotemporal denoising. And the way that works in Teardown, at least, is the spatial part of it is taking 12 samples on a disk shape, like I showed earlier, and then using a bilateral filter to blend the samples of the image. So in this case, it's using planar depth and normals to determine whether 2 samples are similar or whether a sample is similar to the center pixel. And so if either one of these weights or properties are different between the center and the sample, then that means you don't want to blend them, because that'll mean you'll blend over edges, which you don't want. So yeah, and then the temporal part of this is that they reproject the pixel into the previous frame using the motion vector that I talked about earlier. Previous frame colors sampled and then clamped to the min and max color value of the samples taken of the new frame. And this helps minimize ghosting. And then finally, the new and old colors are mixed in a 50% blend to get a temporal accumulation effect. So this is the output of this path. And this is before. Then after they denoise, they modulate the albedo and emissive into the image. So as you probably noticed, there's actually no albedo in these images. It's just like they're just working with pure light values, essentially. And that allows us to filter the noisy input, which is the lighting, because it's stochastically sampled, while maintaining sharp albedo and emissive, which do not contain noise because they're just part of the G buffer. And so this is before modulation, and this is after. The only emissive surface on the scene is this light right here. But obviously the albedo has a big impact. So after that, volumetric lighting is calculated. And it's kind of similar to rendering the deferred lights in that it draws proxy volumes for the lights, as you will see. Yeah, so for modulating the light, someone asked, the formula is really simple. It's basically the final color is lighting times albedo and then plus emissive. And that's the whole thing. The shader is like 10 lines long. And that just makes sure that the albedo and emissive don't get blurred by the denoising filter. Okay, so back to volumetric lighting. So yeah, it's rendered as proxy volumes, just like the local lights. The way this works is that at each pixel that's rendered for the light, a ray will be shot from the camera towards that pixel, or I guess towards the back buffer in that direction of the pixel. And at several points along the ray, another ray will be shot from that point towards the light. And then it'll use a voxel traversal algorithm to determine if the light is visible from that point on the ray. And that information is used to accumulate volumetric light from the light. So all that is done at quarter resolution because it's a low frequency and pretty expensive effect because it's taking a lot of samples per pixel, a lot of raycasts per pixel. After that, there is the volumetric denoising. So before, whoa, okay, I zoomed in a little too much. You have the blue noise, sort of noise. And then afterwards, it's just a simple, basically the shader is a simple blur, an edge-aware blur. So it's similar to the spatiotemporal denoiser that I explained earlier, in that it takes several samples of the current frame and then blends them with a depth weight to make sure it doesn't blend over edges. And then it reprojects the pixel into the old frame using a motion vector to sample an old frame to get additional information. And I do note it's not technically accurate to reproject volumetric lighting because the reprojection is only accurate for the surface and not everything between the surface and the camera, if that makes sense. But it's common to do this in games because it improves the quality and only makes it a little bit incorrect. So, oh yeah, and the brightness between these images is different because they're also applying a distance-based fog effect at each pixel. And then basically that's the bulk of the render, and also where I sort of ran out of time. After volumetric denoising, they have the specular cube map reflection, which the way this works is it takes a sample of a cube map image. So it's similar to a lot of games, and that uses environment image for specular reflections, except for visibility, it uses a raycast. So that way you don't have reflections of parts of the world that cannot be seen or that are like obscured. And then they have another temporal denoising path for the specular reflections. It just blends the current frame with the previous. It's not a spatial filter because a spatial filter would destroy the high frequency detail in the image. So it's just doing spatial or temporal blend. And after they denoise it, they composite the specular lighting onto the image. And so you get the shimmer on the glass, which, yeah, the glass on the floor has a little bit of a specular effect as well. Temporal anti-aliasing. So after after all the main lighting effects, they use full screen temporal anti-aliasing that applies to everything. This is done by taking reprojecting the old or the current pixel into the previous frame, and then searching for well, I can just show the shader actually, or I can describe it. It takes several samples of the current frame to get a min and max of the neighborhood. And then it reprojects into the old frame, takes a sample, and it clamps the sample to the min and max of the new frame. And the idea behind that is to prevent ghosting. And then it just blends the old with the new, and you get a nice anti-aliased image. And if you notice, there's a little bit of a jitter. That is because you want to jitter the projection matrix by less than 1 pixel every frame. And that is how Teardown resolves this checkerboard effect on glass. Because the way glass is rendered is it's rendered as a solid object, but with 50% of the pixels discarded. And so that's how glass is resolved. And it basically denoises the image even more. Temporal denoising is pretty great. And then there's a bloom pass, which I definitely did not have enough time to finish that, but I can show you how that works in a second. All right, so bloom, really bright lights, and it works by downsampling the image several times into increasingly lower resolution textures. So, wow, it's really hard to see. And then after downsamples, upsamples a bunch. And so then you get this nice, super wide blur. And then it gets composited into the image. So I could, okay, so this is definitely the winging it part of this demonstration, but I could get rid of the bloom effect just to see how the image looks without bloom. Oh, and the shader where bloom is composited is also the one that applies tone mapping and gamma correction. Okay, so without bloom, and then with bloom. And after bloom is rendered, the UI is rendered, and that's not super interesting because it's just quads and triangles. And then the final event, the image just gets drawn to the back buffer. So that's mostly everything. I don't think I covered how smoke is rendered, but I could give a live demo of that if you guys want.
Could be cool.
Okay. Let's do this. How the global volume is rendered. I'm not sure what the global volume is. Oh, the shadow volume. Okay, so that's just, it's not rendered, but rather, I believe it's produced by the CPU. So this sort of just represents the state of the world. The positions of all the voxels. Is it done every frame? That's a good, it's probably done every time there's a physics update, because that's when voxels would move. Okay, so opening up render doc right now. Yeah, I just gotta find where Teardown is on my computer. It'll be a second. You guys can feel free to talk, ask questions.
One thing I'm curious about is in this like global texture, there's a lot of like grid patterns in it. Like, is that part of the sparseness or?
That's a good question. Let me close that stuff. So yeah, I'm not 100% sure why it has those patterns.
It looks like they shift though, so maybe it's just a way to, like, even if you miss it in one Z axis, then like the next slice will have it or something.
So one thing that is notable is the fact that obviously this whole volume texture it represents grid aligned voxels. But if you played the game, you know that voxels are not necessarily aligned to the grid. So they must sort of be like rasterizing the voxels to the grid, if that makes sense, to this image. And so maybe these artifacts are caused by like, I don't know if it's a tree or a rock or what, but it might not be like perfectly aligned. And so it could cause some artifacts. I don't know, I'm just postulating.
That could make sense, yeah.
I'm about to launch. Okay. Oh yes, the game runs at a silky smooth 24 frames per second when it's under render dock. So I guess one surefire way to create a lot of smoke is to catch a structure on fire. Wait for the fire to spread a little bit. Then I'll go into photo mode. Oh, it's kind of interesting. When I'm moving the camera, it might not come across with the compression, but when I'm moving the camera, the smoke particles, it looks like they're flowing upwards, sort of in the direction that the smoke is moving. But anyways, take a capture. Which also took a screenshot. So let's see if it actually loads. All right, cool. It's loaded. Oh, okay, I think I see a smoke. Oh wait, no, it's rendered earlier. Oh, it must be rendered in the gbuffer path. There's a lot of objects in here. Oh, okay. I wonder what this red stuff is. Little tiny pixels. It's gonna, maybe it's used for bloom or something. So the actual smoke itself. Fire particle emitters. I'm not sure. Oh wow. Yeah, so the smoke is rendered as a bunch of billboards, it looks like. And you can even see that it's sort of hard to tell. They do follow the direction of the camera, so like a real billboard. But again, it's really hard to tell for even myself, and probably even harder for you guys over compression. So yeah, it looks like the CPU is generating a big mesh.
Is it possible to turn on like the wireframe in the game?
The developers have a wireframe mode in game, but I think that's only in a developer version of the game.
Okay,
But there might be a way. I just don't know it. As far as I'm aware, the actual shading for the smoke is pretty simple. Oh, it's even commented. Fade out close to geometry, fade out close to the camera. It's not doing any ray tracing. I wonder if it's being drawn with what do you call it? Oh, okay, alpha is, there's no blending. Let me confirm that. Blend is all disabled. So it's like completely stochastic. Oh yeah, they're using blue noise to determine whether to, yeah, they're dithering basically. And the fire looks like it's drawn in a similar way. I find it interesting how, oh, and these are also not simple quads. These are,
yeah, just, it's like
I don't know what the shape
Pyramid.
is.
it's
A
like a,
hollow pyramid, yeah. But they are like billboards in the fact that they face the camera, but I guess I'm guessing they do this so they can have sort of more sophisticated shading that makes it look more three-dimensional, if that makes sense.
yeah,
And then, yeah, if you can see temporal blending for sure. When the camera's still, it looks pretty smooth. Also, this is interesting sort of artifact. How the the wire right here, you see like multiple copies of it going up.
Yeah.
I wonder how that is being produced.
Probably because of the motion vectors are pointing upward because of the smoke.
But do you think, I feel like the motion vector should be 0. Oh wait, actually, oh yeah, I feel like in photo mode, shouldn't the motion vectors be, you might be right, actually, let me check. If I can find the motion vectors even. This the one? Interesting. Yeah, it looks like it is writing motion, even when everything's perfectly still. That probably explains the swimming effect when I'm moving the camera. And it explains this whole thing. So yeah, they're writing motion vectors in photo mode, even when everything's still. Huh. Interesting. They get these ghosting artifacts even when there's no motion.
Is it like the motion of the camera?
It's the motion of the camera and the motion of the geometry combined. So the motion represents how many pixels or how far the pixel has traveled between 2 frames. But when literally nothing's moving, the motion should be 0. Oh, and another thing I want to point out is that glass does a number on the denoising and like temporal stability. I have a video. Watch how it wobbles when I'm moving. I don't know if that's apparent over stream, but I guess essentially the reprojection is not accurate because the glass isn't like a transparent surface, but it's like a opaque surface with 50% dithering sort of. And so my theory, at least, is if a pixel gets reprojected onto the glass, then you get like a sort of ugly artifact. I don't know why scrubbing's not working, but yeah. Like I can show that artifact more. Oh, I guess before I show that though, snow. I didn't talk about how snow is rendered, but this is probably also pretty simple. Sort of just exploring it right now. Wow. I guess the snow is just rendered as a bunch of billboards in front of the camera. It's interesting how big the meshes are. Oh, Oh, and here's a texture with smoke and fire and snow and water. Oh, there's a circle and square used for. Oh, and some other stuff. Is there a Google keyword for me to research on how your shadow volume texture works? It's basically just an image of the world. So you just, all the voxels are just rendered to this. Well, rendered probably not the right word. But yeah, on a CPU, you just have some 3D structure that holds all the voxels. And then you would, I guess, somehow copy the voxels to this texture. But it's not so simple because voxels are not necessarily aligned to the grid. As you can see, I can move these around. And if you actually look really closely, the shadow is blocky. And when I slowly move the object, you can see the shadow updates in a blocky way. Or if the door is locked. If I open a door, you can see that the shadow, it updates in a sort of jerky fashion. So that's one thing I don't know for sure is how all the voxels are actually written to the grid, the global grid, that is. But yeah, for how to manage a voxel around camera for voxel ray tracing. I'm not sure what you mean by that question. So yeah, I think the biggest misconception about the renderer of Teardown is that it features global illumination, like ray trace global illumination, which as we've seen, the closest thing is the ambient occlusion, which isn't true global illumination. It's just approximating and then blending a constant ambient color. I also didn't talk about how water is rendered. To recap, the expected reflection or screen space. That's one thing I didn't mention. There definitely is some form of screen space reflection in the game. Although I couldn't capture it in the capture I took of that one scene, but I can show you a different scene where there definitely are specular reflections. Or sorry, screen space specular reflections. So right here, for example, if I look right, the reflection on the door disappears. So take another capture. We can take a look at how that works. Oh, this looks like we're so they sort of do use voxels for reflections, at least for the cube map reflections. They use a voxel ray tracing for determining visibility. So I can show that really quick somewhere. Need to find something. I like the shiny table. You can see the reflection, the cube map reflection is being blocked. So I can prove that's a cube map reflection by looking down. It's really subtle, but you can see this pillar of the window frame. It shows up in the reflection. And I can block it with this object. So yeah, so that's sort of how the voxel ray tracing fits into this. But yeah, then they have specular screen space reflections for more accurate local reflections.
Lumen. We're just talking about lumen.
Mesh distance fields. Lumen is a combination of several techniques. So Lumen has a screen space global illumination aspect, and that's used for emissive surfaces. And it also has, I'm not sure about the SDF stuff, but I know another thing it uses is ray tracing for radiance probes. And they had a cool presentation about that. Maybe I can find it. Oh, the radiance cache. So yeah, nice talk. I'll link that if anyone's curious, check it out. So I'm trying to find where they actually do this, the screen space trace in this shader. So they sample cube map. So I guess they're doing, this is interesting. So it's not really screen space reflection. Well, sort of is, but it's also not. It's screen space, but they're not tracing a ray in screen space. They're tracing an actual world space ray. And then if the ray hits something that is visible on screen, then that means it can take the diffuse color of the thing it hit. I'll definitely have to add that to my write-up. DFAO, out of distance field. Interesting. That's pretty cool. Oh, and I'm gonna link this video where the actual developers of Teardown do a technical breakdown. The first half or so is the renderer, and the second half is the physics. I did not watch the physics part, which is probably would answer some questions about how the whole voxel and grid thing works. I guess I can show some different kinds of lights. Here's some area lights. Kind of cool. It would be really cool if this game had a global illumination, but the way it's rendered, it'd be very difficult to add. Yeah, the game seems to lag a lot more in RenderDoc when it's rendering more stuff. And when I look away and the frustum culling kicks in, and there's very little to render. My FPS goes up to like 120. Yeah, I think this whole entire wall is basically an area light. If you break the emissive surfaces, it should stay the same, right? If you damage emissive surfaces at all, unfortunately, the whole thing. So basically, in Teardown, if you damage a light, the light just turns off. So if I damage this table, the green part turns off. Well, also the purple part. So yeah, that would really throw a big wrench into the renderer. I wonder what happened with this movie screen. So this is supposedly projected as they'd like you to believe, but actually, if you block the projector, nothing happens. So it's probably just one big screen. And indeed, the entire image disappears when you damage it. I'm not sure if that is a spotlight or a capsule light. But yeah, knowing how the renderer works, it kind of lets you figure out what's gonna happen before it happens in terms of lighting. This is one big area light. This pink stuff. I think this white thing is several different area lights, maybe. Or maybe it's just one light. A bunch of small area lights in the bathtub or the spa. Anyone have anything else? Oh, another thing that wasn't shown in my talk, they have this lens dirt effect that only shows up when you're looking at the sun. And the moment you look away, mostly disappears actually, but not completely. It disappears when bright lights are off the screen. That means things like grass are one uniform box or a bunch of boxes stuck together. So that's a good question. Things like grass. Well, for optimal performance, the meshes, so you want to have as little empty space in the 3D texture for each object as possible. That way you can reduce the tracing time. So that means they talk about it in their talk, but like a tree, for example, instead of being one big bounding box with a bunch of empty space on the bottom, they use one bounding box for the trunk that's tightly fitted, and then one bounding box for the leaves and branches. And for the grass, I'm not really sure. I'm gonna take a capture. But the grass seems low enough that maybe it is one big mesh. Oops. It looks like this entire path is one big mesh. This section of grass is one mesh. Oh, yeah, it just looks like it's drawn in chunks, basically. And then these bushes drawn as one box. And then right here is where the depth buffer gets copied. I wonder how they determine that. Seems kind of arbitrary. It's probably based on empirical observations to optimize performance. Yeah, this game does quite a few draw calls. And for every draw call, they do a bunch of GL uniform calls and a bind texture call. So many draw calls. They render all the wires in one draw call. I'm guessing the water is drawn of a single plane. Oh, actually, maybe not, because there's multiple levels of water. Oh, here's an interesting artifact. If I look down, the color from this reflection goes away, but the shape of it is still there. That's because they're using the voxel tracing to determine visibility. So for the cube map reflection, it's still blocking, but it no longer has a screen space information for color. So yeah, they have water right here and also water over there. Yeah, I feel like you might be able to get some sort of reflection by, because I believe the well, it'd be difficult, but the volume texture does. Oh wait, that's not the right one. It does encode the material kind of. But I guess it doesn't have enough information to actually get the color of the voxel just using this image. But you can get some information about the material. It makes sense that all the maps are kind of flat. Because if there's a lot of variation in height, then there would be an issue with wasted space in this texture. This is a pretty, do some math. This is a 0.5 gigabyte texture. And then if you include MIPS, it adds like another 12% on top of that. Yeah, I mean, if you don't have 0.5 gig of VRAM to work with, then you probably can't run this game anyways. Oh, this diving board actually has physics. Nice. To each of the props in the scene, do they share textures? So they have like a global set of material textures that all objects share, but each object has its own little volume texture. So like, although these chairs are identical, they have a separate volume texture, as far as I'm aware anyways. because they can change individually. So now these are definitely two different textures of volume. I think that's everything for teardown. So now you guys can go and create your own teardown clone, at least in terms of rendering. No promises on the physics aspect. I don't know how that works, but the physics seem pretty good. Do you guys want to talk about GP graphics programming weekly?